All right, so this is passage 5. This is question 25 of that passage. And it states here that based on information presented in table 1, which relationship between pH and charged functional groups is accurate? So let's take a look at answer choice A. It says at pH 8.5, the ratio of the cationic to anionic functional groups in the NQRD subunit is equal to 1. So let's take a look. NQRD is right here. What we'll notice here is that the PI is given in this column here. And we'll notice the PI for NQRD is 8.5. So what exactly is PI, guys? This is a really important concept you need to know, and that's the isoelectric point. What is the isoelectric point? That is the point in which you have a Zwitter ionic form of an amino acid or some kind of peptide. And what does that mean? That means the overall charge of that amino acid, for example, is 0, or the entire peptide's charge is 0. So that doesn't mean every single functional group has a charge of 0. That means that if you have one functional group that's +1, then you have to have another functional group that's -1, so that they add up to 0. So let's take a look. It says at pH 8.5, the ratio of the cationic, remember the cationic means plus, and the anionic functional groups, so that's minus, in the NQRD subunit is equal to 1. Now proteins are always +1 or -1, and so that means if you have an equal ratio of +1s and -1s, your sum of these charges is going to be 0, aka that's your PI. And since we look at this table, we know that NQRD's PI is 8.5. A has to be a correct statement. But let's take a look at B, C, and D. B says at pH 7, half of the functional groups in the NQRE subunit are protonated. Let's take a look. Or sorry, NQRE. So we have a PI of 5.35, and so a pH of 7 is greater than 5.35, which means you're going to have more deprotonated groups than protonated groups. Here it says half the functional groups are protonated. We don't know anything about what number of functional groups in NQRE are protonated. At pH 7, you just know that it's greater than the PI, which means overall you're gonna see a lot more negative charges associated with NQRE subunit. You don't actually know if half of the functional groups are going to be protonated. Now, another reason why that's wrong is if half of the functional groups are protonated, that either means the other half are deprotonated at best, or the other half is going to be neutral. If the other half is deprotonated, right, so if one half of them are protonated, +1, and the other half are deprotonated at -1, this is the Zwitter ionic form. This is when your charge all adds up, the PI point where the charge all adds up to 0. Well, we know that the PI point is actually 5.35 for NQRE and not 7, which means this can't be a possibility. If half of them are +1 and half of them are neutral, that means you're just going to have an overall +1 charge on some kind of positive charge, positive X charge on NQRE's subunit, or the NQRE subunit. But like I said again, if pH is greater than the PI, that means overall that subunit has to be somewhat negatively charged. So these two scenarios are impossible, which basically means that B has to be an incorrect answer. C says at pH 6.3, the net charge of the cationic and anionic functional groups in the NQRA subunit is equal to 1. Let's take a look at NQRA. So again, PI is 6.3. Guys, remember, if the PI is 6.3 and you're at a pH of 6.3, the net charge is going to be 0, not 1. So C has to be incorrect. And finally, D, it says at pH 6, the majority of the functional groups in NQRF subunit are protonated. All right, NQRF. This is the PI. Again, if the pH is greater than the PI, the majority of your group is going to be deprotonated, okay? So D has to be incorrect since it should be deprotonated, not protonated, leaving A as the correct answer for this question. All right, so this is question 26 of passage 5. It says, what is the most likely effect of adding a sodium ionophore to a culture of V. cholerae? So what is a sodium ionophore? This is going to be something that is not really explained in the passage, so I'll just tell you exactly what this really is. An ionophore is something that carries, sodium ionophore is something that carries sodium from one side of a membrane to the other side. So let's take a look at what sodium does for this V. cholerae. All right, let's take a look. In this paragraph, we see that we have an electrochemical gradient of sodium known as a sodium motive force. Guys, this should immediately bring up the proton motive force in our bodies. But here we see that instead of protons, we have sodium instead. And this provides the V. cholerae with the energy of four key functions. So just like the proton motive force, which provides ATP for us, this sodium motive force is also providing some kind of energy for this species here. It's established by this Na plus NQR enzyme, so that makes sense, just like, oh, actually, it goes on here. In a similar process to proton pumping by complex 1 of the ETC, this thing couples the movement of electrons from an NADH donor with ion transport. So what does that mean? It means it moves sodium across against the concentration membrane, or the concentration gradient, by using NADH's reducing power to do so. So all of this should look really similar to what our ETC and ATP synthase does, except instead of protons, we're using sodium. So let's take a look at the question itself. So what is the most likely effect of adding this sodium ionophore to a culture of V. cholerae? Let's illustrate what we have going on here. We have this membrane, and on one side, or I guess we have the Na plus NQR, and it's working really hard to pump Na plus onto this outside area here. And so there's a lot of Na plus here, okay? And similar to the protons, this Na plus likes to go down its concentration gradient, okay? And as it's going down its concentration gradient, it's going to go through, let's see. Well, it doesn't exactly say here, I guess, but it does go through this protein, and we know that it provides some kind of energy. Now, we can presume that this energy is probably going to be in the form of ATP, okay? If this is exactly similar to exactly what our ETC and ATP synthase process looks like, except for protons we have sodium, then we can reasonably assume that the energy that they form is going to be ATP. But to double check, let's take a look at the answer choices here. So if we add a sodium ionophore, what's going to happen? Let's say we open up a hole. Okay, so this is our sodium ionophore, and it's essentially you're creating a hole here that the sodium can go through. So now the sodium, instead of going through this energy making device that if the sodium goes through, ATP will be formed, they will actually just go down this other hole as well. So maybe some of the sodium goes through this guy, some of the sodium goes through this guy. What we have in general is that sodium is not going through this energy forming machine here, and that means we're going to have less energy since we have a hole in the membrane, disrupting the sodium concentration gradient that Na plus NQR is trying so desperately hard to establish. So A, decreased activity of Na plus NQR. If we add this sodium ionophore, that's not going to change how this is going to act. This is just going as hard as it can. It's just going to try to establish that Na plus concentration gradient as hard as it can, regardless of whether or not that sodium is slowing back down or not. This entire job is to establish that Na plus concentration gradient. So the sodium ionophore is not going to really affect the activity of Na plus NQR. If anything, it's going to increase its activity since there's going to be less sodium formed on this side of the membrane, meaning this is going to want to work a little bit harder to get that sodium up onto this side of the membrane. Now let's take a look. I'm actually going to skip B here. I'm going to go take a look at C and D. C says decreased pH of the periplasm. Guys, remember, we're not working with protons here like we are in the human bodies or the human mitochondria. We're working with sodium, and sodium doesn't affect pH, not by itself directly at least. And if we look at the rest of the passage, we don't really have any idea if protons really come into play in this specific species here. So C is probably not going to be the answer choice here, and D, decreased consumption of O2. Guys, we don't actually know if O2 plays any role. Now, in our human bodies, O2 is used in the ETC pathway to get protons across the membrane, but here we don't have any indication of O2 being used, so we don't actually know if D is going to be one of the correct answers, and it's not supported at all. B is the best supported answer, decreased production of ATP. Like I said, if you have less sodium going down through this machine, you're going to form less energy. Remember, the paragraph tells us here that this sodium motive force provides us with energy, and that energy is likely going to be in the form of ATP. So using those assumptions and the connections between this entire system and this mechanism with the proton motive force, the electron transport chain, the ATP synthase in the human mitochondria, we can presume that with decreased amounts of Na plus flowing through this machine, because of this hole that allows the Na plus to go through, because you have less Na plus going through this machine over here, you're going to form less energy, which in turn basically means you're forming less ATP, making B the correct answer here. This is the third question of passage 5, or question 27, and it says, which two subunits of Na plus NQR can be separated by gel filtration, but not by ion exchange chromatography? So what is gel filtration? This is when you separate by size, okay? And ion exchange chromatography, this is when you separate by the PI, or the difference in charges at various pHs, so basically PI. Guys, remember, just a side note, when pH is greater than the PI, you're going to be negatively charged, and if pH is less than the PI, the protein's going to be positively charged. So this is how we separate out different proteins with different PIs. You can use a pH that's in between both of the PIs, so that one is negatively charged, or one protein is negatively charged, and the other protein is positively charged. But that's just an aside for now. So let's see which two subunits can be separated by gel filtration. So A says NQRA and NQRB. So technically they do have different molecular weights, okay? But you have to notice, or you have to keep in mind one thing: for gel filtration, there has to be at least a 1 kilodalton difference between the two species you're trying to separate in order for that gel filtration to successfully separate those proteins. So obviously here we don't have 1 kilodalton difference in the weight. We only have 0.2 kilodaltons. So that means NQRA and NQRB cannot be separated by gel filtration. They'll just kind of flow through the column together, and you won't be able to tell whether your solution has or your elution has both NQRA and NQRB or just one or the other. So A cannot be the correct answer. B says NQRC and NQRE. So the C and E, we'll take a note. This one does have a substantial difference, okay, in the kilodalton molecular weight, which means they can be separated by gel filtration. But remember, we're looking for something that's not going to be separated by ion exchange chromatography. So we want something where their PIs are very similar, okay? And we'll notice these PIs are very different, which means they can be separated by ion exchange chromatography. For example, if I set my pH to something like 6.5, well, NQRC, because the PI is less or greater than the pH, it's going to be positively charged, whereas NQRE, because the pH is greater than the PI, the NQRE subunit is going to be negatively charged. So you would be able to separate out NQRC and NQRE with ion exchange chromatography. So C, because we're looking for something that cannot be exchanged or separated by ion exchange chromatography, B has to be incorrect. Now let's look at D and F. D says we have a molecular weight of 22.8. F has 47.1 kilodaltons, so we know that they can be separated out by gel filtration. Let's compare the PIs. Again, the PIs are too different. This tells us we can separate by ion exchange chromatography, and we're looking for something where you cannot separate using ion exchange chromatography. So that means C has to be incorrect as well. Finally, that leaves us with E versus F. If you look at E and F, we'll notice, look, they're kilodaltons, very different. You can separate them out with gel filtration, aka size exclusion. But let's take a look at their PIs. They're very similar. I guess I've really covered this one up, but this one says 5.35 and this one says 5.25. Their PIs are extremely close to each other, which means what? It's going to be very, very, very difficult to separate these proteins out just by using ion exchange chromatography. And because the question is asking for something where we can't use ion exchange chromatography, that means D has to be the correct answer here. All right, let's take a look at the last question of the passage, and it says, which enzyme of the citric acid cycle is not directly involved in generation of the dinucleotide required for Na plus NQR activity? So what does Na plus NQR require? Requires NADH. Oh, yeah, there we go. It requires NADH, okay? So this is the dinucleotide they're talking about, the nicotinamide adenine dinucleotide. And here we actually have a structure of NAD plus, right? So this is NAD plus / NADH. It's one or the other. Well, this in particular is NAD plus, but you add a hydrogen or you reduce it one step and you get NADH. So this is the dinucleotide they're talking about, okay? And so we're looking for an enzyme of the citric acid cycle that does not generate NADH. And here we go, the citric acid cycle right here. Remember, you guys have to memorize this citric acid cycle. All of the enzymes, all of the products, the reactants, the side products like the CO2 plus or CO2, like things like that. Just memorize as much as you can about this cycle because this is 100% fair game for the MCAT. So let's look for the enzyme that doesn't produce NADH or NAD+. Malate dehydrogenase, we see over here, produces NADH. Succinate dehydrogenase, let's take a look over here, does not produce NADH, produces FADH2, so that's pretty promising for now. Isocitrate dehydrogenase, we'll take a look over here, produces NADH, and finally alpha-ketoglutarate dehydrogenase produces NADH. So because A, C, and D all produce NADH, which is required for Na plus NQR, succinate dehydrogenase produces FADH2, which is not required for Na plus NQR. That makes B the correct answer for this question.